In this video, I just want to take a look at a couple of theorems related to linear independence. The first one is about small sets. The fewer things you have in the set, the more readily you can determine whether the set is linearly dependent or independent. In particular, the zero vector is a teller, right? If you've got the zero vector in your set, it has to be linearly dependent. Because if you have something like, you know, K1 V1 plus K2 V2 plus and so on, and let's just say the last one is the zero vector. Again, it doesn't matter what order you put them in. So I have K n times 0. And I want to say, is it possible to get that to add up to the zero vector without all of the k's equaling 0? It's like, well, yes, it is, because you could just set this k to 0 and this k to 0 and all the other k's to 0, except the last one. Let's make it 7, right? Because 7 times the zero vector is the zero vector, plus all those other zeros would be the zero vector. I would have a linear combination that adds up to the zero vector where not all of the coefficients are 0. Some of them are, but not all of them, because the coefficient in front of the zero vector here is something other than 0, but that doesn't matter because when you multiply by the zero vector, it'll be 0 and it all adds up to 0. So this definitely is the case. If your set contains a zero vector, it is linearly dependent, not independent. Okay. If your set has exactly one vector, then it's linearly independent if and only if that vector is not the zero vector. Right? Because if you look at just one vector and you look at k1 v1 equals zero vector, how could that be? Well, it would either have to be that v is the zero vector or that k is 0, k1 is 0. Well, if you don't have the zero vector, then the only way to do this is your coefficient has to be 0, and so that vector by itself is independent. One vector all by itself is independent, unless it's the zero vector, in which case it's dependent. And then the third part here, a set with exactly two vectors is linearly independent if and only if neither is a scalar multiple of the other. This seems to me like this is definition, I think what I call definition 2 in the previous the previous video, that if you only have two vectors, it's linearly independent if none of the vectors is a linear combination of the others. So it's linearly dependent if one of them is a linear combination of the others. So if you had V1 is a linear combination of V2, well, there's only one here. I can't add a bunch of things together because once I got V1 on this side, there's only one vector left. And so the linear combination of that vector is just multiplying it by a constant. So if you can do this, if you can write V1 as a linear combination of V2, as a scalar multiple of V2, then you are dependent. If you can't do this, then you must be independent. So when you only got one or two vectors, it's pretty easy to see. In particular, if you're, again, I always picture vectors as arrows or pairs or triples of numbers, but we got all kinds of vector spaces now. So for instance, your vectors might be functions. And what would it mean if you had two functions? What would it mean that one is a scalar multiple of the other? Well, it'd be like sine x and 2 sine x, right? You just multiply one of them by a scalar to get the other one. So sine x and 2 sine x are scalar multiples. That is, the second one is 2 times the first one. Right? But graphically, what does it mean? Could you recognize, if you looked at the graphs of the function, when one is just a scalar multiple of the other? Well, yes, I think you can, because multiplying a function by a constant, right? If v2 is just some function and you multiply it by some scalar k2, whatever graph you had before, the multiplying by a constant out here in front scales the thing in the y direction, right? That the the zeros would still be in the same place. If I can do this, there we go, right? So the one vector, the one graph would just be scaled up by a constant factor, not shifted, but scaled. So graphically, it would be, I think, pretty straightforward to see that one was a scalar multiple of the other. Sine and cosine are independent of each other, because if you look at the graph of sine, and you look at the graph of cosine, something like this, right? One is not scaled from the other, one is shifted sideways from the other. So it is not just multiplying by a scalar. So sine and cosine are not dependent, they must be independent. Okay. Now, the second theorem we want to look at here is not just any old vector space, but Rn. And it says if you've got a set of vectors, v1, v2, up to vr, and they are in the vector space Rn, then if R is bigger than n, so let's say n was 3, we're in R3, and so R must be 4. So if you have 4 or more vectors in R3, then we're saying you must be linearly dependent. Okay. So the book gives a written out proof. I'm just going to essentially sketch it. I'm thinking of each one of these vectors here. V1 is the vector v11, comma, v12, comma, up to, we're in Rn, so this must be v1n, right? There's n coefficients. And so on down the line, where vr is the vector vr1 first component, vr second component, up to vr nth component, right? So each one of those vectors, if I look at the way I'm going to describe them is in terms of these double subscripts. The first subscript tells you which vector you have. The second subscript tells you which coordinate you're in. Okay. So if I want to see whether these vectors are dependent or independent, I would look at k1 v1 plus k2 v2 plus all the way up to kn. No, how many of them are there? There's r of them, so this is kr dr. Right? And I want to see, can I find a way to add that up to the 0 vector where the k's are not equal to 0? Some of them might be 0, but as long as one of them is not 0, then I'll have found a way other than having them all 0. Okay. Well, the thing is here, we're in Rn, so this single vector equation actually corresponds to n real number equations, right? The first equation would be the first component here. So the first component, when I add up everything on the left-hand side, would be k1 v1 first component plus k2 v2 first component plus all the way up to kr vr first component. And that has to be the first component of the 0 vector, but of course that is 0. And likewise, second component would be, so k1 times the second component of that, so that would be v1 second component, plus k2 v2 second component, plus all the way up to kr vr second component. And then keep going, dot, 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 down to the last one. What is the last one? Well, each of these things has n components in them. So the last one would be k1 v1 nth component plus k2 v2 nth component plus all the way up to kr vr nth component, and that has to be 0. So what I have here is a system of linear equations, right? The variables are the k's, because all the vij's are just the components of the given vectors that you started with up here, right? So I have how many equations? Well, it looks like I have 1, 2, 3, I have n equations. How many variables? Well, I have 1, 2, up to r. I have r unknowns. If I have more unknowns, r is bigger than n. If I have more unknowns than equations, and it's a homogeneous system, which it is, right? These are all zeros over here on the right-hand side. It's a homogeneous system. You know it has at least one solution, but because there's more equations than variables, because there's more variables than equations, when you make the augmented matrix and put it in a reduced row echelon form, you'll definitely have a column that has no leading ones. You've got a free variable. You've got infinitely many solutions, which means there's solutions other than having all of the k's equal to 0, and hence they must be dependent. So in R2, If you've got 3 or more vectors, in R2, if you have 3 or more vectors, they have to be dependent. In R3, if you have 4 or more vectors, they have to be dependent. Now, this says nothing about when R is less than or equal to n. So if you're in R3 and you've got 2 vectors, are they dependent or independent? You don't know. They might be pointing in the same direction. They might not be. Right? So at least we know if you have more vectors than the n here of Rn. If you got more vectors than that, they have to be dependent.